Hello, today I'd like to talk about how data are stored on computers. They're really integers, and that's what we're going to talk about. Integers can be represented in many different bases. Everyone's comfortable with base 10 decimal, but really need to study base 2 binary and base 16 hexadecimal. Integers are actually stored in a binary format, and whatever programming language you're going to deal with uh, basically shows those as decimal. We're going to discuss the hexadecimal equivalents. We're going to look at the various representations and sort of pick them apart and show that they're equivalent. We're going to talk about signed integers versus unsigned integers. We're going to start with 8-bit numbers and then we'll extend. And then I'm really happy to show you an example with real implementation with physical meaning. Integers are stored as binary numbers, and it's a sequence of ones and zeros called bits. A sequence of 8 bits is called a byte. Like decimal, there's bit positions that are going to be orders of powers of 2. As an example, left to right, they're going to be descending powers, and then right to left, ascending powers. So let's focus on right to left. So the ones place would be 2 to the 0. 2 to the 1 would be 2's place. 2 squared is the 4's place. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. 2 to the 7th is 128. So those are the positions. And what we do when we're showing something as a binary, we'll go ahead and identify that with a 0B in the front, just to make it clear that that prefix means that what follows is a binary number. Okay, so let's see what this binary number equals. Well, there's 1 2 to the 6, I've got that. There's 1 2 to the 4th, I've got that. There's a 2 to the 2 cubes, I've got that. 2 squared, I've got that, and then 2 to the 0, or the 1, I've got the 1 there. And when we add those up, we can look at the decimal equivalents of them. 2 to the 6 is 64. 2 to the 4th is 16. 2 cubed is 8. 2 squared is 4 plus 1. So that's 80, 92, 93 decimal. Okay, so 93 decimal is that binary sequence. Let's go find out what the hexadecimal equivalent is. It's very straightforward. What happens is you just group 4 bits together and call that a nibble. So that lower nibble there, we're going to call that D. We'll show you why. And the upper nibble, we're going to call that 5, and we'll show you why. So that's a hexadecimal number. We'll call it 5 dog. And we get a helpful prefix again with the OX. And what you need to think about is how the binary nibbles will match up against the corresponding hex digit. And let's focus on 5. So 5, these places are the binary places. So the 1's place, the 2's place, the 4's place, the 8's place. So when I get down to the 5, I've got a 4. I've got 1 in the 4's place, and I've got 1 in the 1's place. So 4 plus 1 is 5. So that's why that's 5. So in hex, normal decimal, you've only got 10 figures that you can show 0 through 9. But in hex, we need 6 more. So what we do is we just start over and call it out A, B, C, D, E, F. So that gets that coupled with our normal 10 figures, that gives us the 16 figures that we need. Let's go take a look at the dog line. So we've got a 1 in the 8th place. We've got a 1 in the 4's place. So that's 12. And then we have a 1 in the 1's place. So that's 13. So dog represents 13. So the takeaway here is that 93 decimal is the same as 5 dog hex, is the same as 0101, 1101. So that helpful syntax, sometimes I'll add a D there, but it's just a basis, it's just a change of basis representation. All these really represent the same number. We've got the 1's place here for base 16, and here's a 16's place for base 16 or hex. So there's a direct association between base 2 and base 16. It's just a matter of partitioning in 4 bits, in groups of 4 bits. And that's all it is. Very straightforward to go back and forth between binary and hexadecimal. Very straightforward. A little more indirect to get from those the binary and hex over to the decimal. A little bit indirect associated. And of course, that's the ones place, and then that's the tens place. Okay, so the number 93 decimal is shown, as I showed you, with this binary sequence of bits, and we add that 0B there in front to make sure everyone's clear. Yeah, that's a binary number. We really can't show binary numbers when at the command prompt of a MATLAB. So what we do is we use a character array, and there's a function in MATLAB called decimal to binary, and I'm putting in my 93 right there, and I'm telling it I want 8 bits, and I just called it a variable there. So it gives me that sequence of bits that we've been talking about. What I like to do is to add that that prefix there, and to do it, I just concatenate it very simply. I do a single tick, 0B single tick. So that's a character array that I concatenate with the character array that would be here, and I get the desired result. Okay, so you end up there with 10 digits because you have 10 figures in our character array, because we've got our OB, and then we're followed up by the bits in a descending sequence. So because of that, when we go try to index through that bin 93 with the prefix, when we index through that, the first one's going to be an O, the second one's going to be a B, the third one's going to be an O, the fourth one's going to be a 1. So we're just walking through it, and the fifth one's going to be a 1. 1, 2, 3, 4, 5. I'm sorry, the fifth one's going to be a 0, 5. And then kind of carrying on here, 6 is a 1, 7's a 1, 8's a 1, 9 is a 0, and 10's a 1. Kind of just brute force going through there with the parens to index into that array. Or I could create a little script here, a script 0. I've created my bin 93, and I'm just going to walk through it. So I'm going I equals 1 to 10, because length of bin 93 is 10. And I'm just going to display bin 93 with whatever I it is and the value of that character. So that looks like this when you print it out. So important to kind of recognize that the LSB, or the least significant bit, comes last. And the most significant bit's actually coming sooner, and it's the third one, because we've got the 2 prefix characters. All right, let's look at how we can sort of go the other way. We take our binary sequence of bits, and we go and try to figure out, well, what's the number? And how I do this is I create the sequence of bits here, and then I kind of print it out. I have this flip function because what I'm going to do is I'm actually going to start from the lowest bit. I'm going to start from the lowest bit and then build it towards the most significant bit. So I flip it. Don't have to do this, but it does make it a lot easier to kind of manage. So I flip using the flip function, so it reverses the order of the bits. So the lowest significant bit would be coming first. And that would be when I equals 1. I'd actually be hitting that. So I'm going to go I is 1 to the length of bin 93 minus 2. So I'm going to go 1 to 10 minus 2, which is 8. So the first time through, I'm going to get the first bit, the least significant bit, and I want to multiply that. If I have that bit turned on, I want to add in 2 to the I minus 1. So that's going to be 2 to the 0 first time through, because the exponent that you're wanting to utilized is actually diminished by 1 from the particular I slot. Okay, and then I'm going to just sum it up. So no multiplication here, actually. I'm just going to do 2 to the I minus 1 if that bit is set. And then I'm going to display it. Okay, so start with a sum of 0, and then I just kind of accumulate that sum, and then at the end I print it. So that's kind of the idea here. Let's see how it works. So when I run it, I get this result. The bin 93 is in the correct order. When I flip it, it's backwards with the B0 on the end. Everything's completely backwards. And then I walk through the bits in that order and accumulate the sum in this way and get the 93 back. So that is going through in a binary way. Okay, so flipping it, and again, just the reason I flip it is so it just makes it much easier to kind of accumulate that sum based on the I and based on the 2 to that I minus 1 exponent. I didn't have to do that. I could have done some finagling where I went with in the reverse order, maybe I equals 10 and kind of walk backwards. But this is a much easier way of doing it. Let's look at hex. So now for hex, I'm going decimal to hex, and I've only got 2 digits for that. So it's going to be OX 5D, as you know. And then I flip it, so it should be dog 5XO after I flip it around. Same thing, I'm going to sum it, and I'm going to go length of hex 93 is going to be 4 minus 2. I'm going to go 1 from 1, I equals 1 to 2. And check this out. Now I've got to figure out what my current nibble is. So I'm going to have to create a function, get hex nibble, and I'll show you that in a minute. So get hex nibble, and I'm going to give it the flipped nibble, the flipped character coming in out of that array, the ith one. And if that cur nibble is greater than 0, I'm going to go cur nibble times 16 to the I minus 1. Remember that our I is going from 1 to 2 in this case, but I want the exponent to go from 16 to the 0 to 16 to the 1. So it's I minus 1 again, similarly to how we did our binary version. Okay, and I'm going to add that to accumulate that to the sum, and I'm printing it out, and then I print out the final. So that's how it works. And start with the hex 93, getting that from the decimal to hex, as we're used to. Then I flip it around, and then I walk, I get the 13 first because the D is coming off first, and that'll be times 16 to the 0. And then I add in 5 times 16, which is 80. So it works out well. Now let's, again, reversed order. Started with the LSN, least significant nibble. All right. So now you talked a little bit about the get hex nibble function. It's pretty straightforward. So get hex nibble, I'm bringing in a character, and I want to return a value. So if the character were 5, I'd want to return the value of 5. If the character coming in is a dog, D, I want to return 13. And it could be any of the others, obviously. But I wanted to show you the use of this really, really powerful control flow. Keyword is switch. So you have switch and you have case for the various cases that you might need. And I always stick an otherwise in there in case something will really blow up. At least I'm providing an answer. But generally speaking, we're coming through with a 0 through an F. And we should be responding with the appropriate numerical value there, right? So that's how get hex nibble works with the switch statement. You could use it. This is much better than using an ugly bunch of if, else, if. It's if, else, if. So you could just repeat. Instead of switching on the hex char, you could just repeat the else if hex char equals 5, you're returning 5. Else if hex char equals dog, you're returning 13. So same, these are equivalent, and sometimes folks are more comfortable using if, else if, it's else if, or else if, else if, else if, and then at the end you'll have an else for the final one. Okay, so wanted to show you that. Okay, so for base conversion so far, we've converted from binary to decimal, really the character representations of it. We've converted from hexadecimal to decimal. And now we want to think about creating our own decimal to binary character, if you will, or decimal to hex. There's two ways of doing this. Wanted to show you both. So to do that, I want to show you about let me go back. There's you could use the remainder function, the modulo remainder function, and with a floor function, or we could use a bitwise mask with the and then a bit shift. So these two are equivalent, and I wanted to show you both of them. So remainder. So this gives you the remainder after you do a division of two numbers, say typically integers. So for here, if I went remainder of 93 divided by 16, well, you know that 16 goes into 80, so that means that the remainder is going to be 13. That's how it works. And then the floor would actually kind of give you the other value, so it's going to round it down. So if I got floor of 93 divided by 16, you know, that would be 5 and 13/16, right? So it's going to floor that. So it's going to come down to the next lower integer, which is 5. So that's what you do, is you go remainder, floor, remainder, floor. Okay, so let's look at this, and we could write our own decimal to hex function. We could give ourselves some hex digits. So we have 16 hex digits right there, starting at 0. And then we do our remainder function to get our 13 right there. So our 13 is going to be our LSN. And since we're going to be pulling out hex digits, LSN plus 1, so that's going to be 14, right? 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, they're all off by 1, right? So that's why I have to add that 1 in, because we start at 0 in this hex digit array, and then we need to add 1 to get the character we want. So then my MSN is going to be the remainder after flooring 93 divided by 16. So I assign that to some temp variable, and I do a remainder again. So you know MSN is going to be 5, and I do 5 plus 1. 1, 2, 3, 4, 5, 6. So the sixth place will give me the 5 character. OX5 dog is what it's going to be. OX5 dog, as you know. Okay, so we could write our own decimal to binary function, and I build it similarly. I'll build it backwards. I'll start with my value. I'll start with my binary character string as an empty. The tick tick means there's nothing in it. It's just empty. I'm going to go from I equals 1 to 8, and I'm going to do remainder of the value divided by 2. So that's going to either be 0 or 1. So if it's greater than 0, I'm going to take the bin string that I had before, and I'm going to append a 1 to it, because whatever I iteration I'm on right now, that first time through, for example, value would be 93. And when I take 93 and do a remainder divided by 2, I'm going to get a 1 because it's an odd number. So that's pretty straightforward. So I would get the 1. As you know, the LSB is a 1. And then after I do that part, I'll update the value. I'll take the value that I had, and first time through is 93 divided by 2. So that's going to be 46.5. When I floor that, I get 46. So then value is going to be 46 on the first time through before I go and increment I to 2. All right, so then here I display it. I'm just going to display my current I. I'm going to display the value, my current value at the end of the for loop, and then I'm going to print my bin, the bin that I've accumulated so far. All right, and then when I'm done, since my bin is backwards, I'm going to flip it and then do a prefix of my OB. So that's all I need to do. Let's see what happens. I run it. So I call this script 4. First time through, as I was saying, my value at the end of the first loop is going to be 46, and the bin is only going to be 1. That's all I've got. And then slowly but surely, I append whatever bits I need until I get all the way to the end. And this is dog backwards, and that's 5 backwards. And then I flip it around, and then I do a prefix of OB. So that's how it works. And so that's with the remainder floor technique, okay? So we want to get to where we're manipulating bits and comfortable dealing with bits. So if I wanted to do a bitwise AND, that's the same thing. If I do bit AND of value, bitwise AND of value in 1, that's the same thing as looking at the remainder of dividing the value by 2. These are exactly the same. And the floor of a value divided by 2 is the same as doing a bit shift of my value 1 spot to the right. Okay, so we're going to go a deep dive here and see what this does. And it's really exactly the same output that we had before, called the script for B. All right, so for bitwise AND, let's go and take a look. Just take 2 bits. If you take an A bit and a B bit, if they're both 0, then A and B, 0 means false. So if they're both false, you got a false. If B is true but A is false, you're going to be false, because false and true is false. True and false is false. True and true is true. So only when both bits are 1 are you going to have the result of the AND function be a 1. If we look at taking the first time through that loop, and we've got the 5 dog, and we're going to bitwise AND that with just a 1. And what that means is all of these, it doesn't matter. It makes no difference what these values are here, because all of these are 0. So that means the result will have all of these as 0. And this, whatever the result is here, is going to be controlled. Since that's a 1, this value will be whatever that very last bit is. So that's called a mask. That's a mask where you take this all zeros and you have a 1 bit on the end. You're basically masking off all of that and grabbing that 1 bit. Okay, so bitwise AND with that 1 in the 1's place is just like the remainder dividing by 2. So that's all it is. It's a masking function. It gives you the values of where you have those 1's on. Okay, so let's look at a shift now. A bitwise shift function is where you take all your bits and you move them one way or the other. A left shift would multiply by 2, but a right shift that we're going to do now, typically shown with the double greater thans, that would be a right shift. So you take the 5 dog that we had before and you shift it right 1 spot. Then you're going to put in a 0 there, and you're going to backfill a 0. But that 0 goes there, that 1 goes there, 0, 1, 1, 1, and that 0 there. That 1 gets lost, it drops off. So that 1, the negative 1, means you're shifting it to the right, and the 1 that you had in the 1's place is gone. A negative shift bits to the right. Okay, so it's, when you shift it to the right, it's just like dividing by 2, because you've just reset the places, the 2's place of every number. Okay, now let's take that thought and mature it to handle hexadecimal. It's very straightforward. For our least significant nibble, we will take 93 and mask it with 15. So that means we're going to mask it with all of the 4 bits active. If you go back and think about this table here, all bits are on for that fox, that 15. Okay, so we're going to do a bitwise AND of 93 with 15. So you're masking off all 4 bits, that least significant nibble. You're masking off the bottom 4 bits of the whole value. Okay, and then here you're going to shift it. You're going to shift it to the right by 4 bits. So you're going to be dividing 93 by 16. And then you do the bitwise AND again. So this is how you do it. And I just wrote a script 5 that would run this. So and I took away the semicolon so you could see the result. So the least significant nibble, comes through as 13, as you know. And the MSN comes through as 5, as you know. So that gives you the 5 dog. So very, very mature way of sort of extracting the data that you need. You mask it with 15, and that gives you the least significant nibble. And then you take what you had and divide it by 16 so that you're shifting down to get what would be the next nibble the next time through, which is that. Okay, so we've done a lot here. We've talked about integers. We've talked about how they're stored as binary, discussed hexadecimal equivalents, and then we went back and forth from the various representation. Now I want to talk about signed versus unsigned. So signed versus unsigned. So if it's unsigned, we've talked about already, but if it's signed, there's 256 things either way you go with 8 bits. So either you're starting at 0 and going up to 255, that's unsigned, or you're starting at minus 128 and you're going through to plus 127. So that's what you can do for 8 bits. If it's 16 bits, you start at, if it's unsigned, you start at 0, and then you go up to 65,535. And if it's signed, you start at minus 32,768, and then you go towards 32,767. So you have 65,536 number of things. That's 2 to the 16. And then whatever bits you come up with, there's a similar pattern between going from unsigned to signed. It's the same similar thing. So let's take a look at 8-bit data. It could be signed or it could be unsigned. Like if you're given a sequence of bits and the corresponding hex equivalents, that same data could be signed or it could be unsigned. Now, if we look at our 5 dog is giving us a 93 for assigned, but that's also, it's the same, it's within the same unsigned type of area. When I get to 127, which is 7 foxtrot, if you look at the binary, it's 7 foxtrot. If I look at that, that's 127 signed, and it's also 127 unsigned. If I add 1, if I treat it as unsigned, and I add 1, I'm going to get 128. Okay? And I can't do that if I'm treating it as signed. 128 is 80 hex, or 8, with everything else being 0. So, and you could think of that 7F. If I add 1 to 7F, 7 foxtrot, if I add 1, that's going to make that a 0. I'd carry the 1. It's going to make that a 0. Carry the 1. It's going to make that a 0. Carry the 1. It's going to make that a 0. Carry the 1. It's going to make that a 0. Carry the 1. It's going to make that a 0. Carry the 1. It's going to make that a 0. Carry the 1. So it's just like an addition that you learned in first, second grade. Yeah. So anyway, but when I get to this 80 hex, I could treat it as unsigned, no problem. But if it were signed, I would do what's called a overflow. It would actually overflow, and it would go back to minus 128. So one good one we could look at would be this minus 93. This bit here, if it is signed, if the number is signed, this bit is the signed bit. Okay? But what we're going to do is we're going to take a look at this minus 93. Since we're so comfortable with 93, let's go look at minus 93. Okay, so minus 93 is able 3, A3. It's able 3. And if I were to treat it as unsigned, it would be 163. So there's two ways I can get the able 3 from minus 93. Let's take a look at those. So the first way, and I think everyone would have gotten this, I could add 256 to minus 93. I'd get 163, and then I would just do the same thing I did earlier in order to figure out it would be able 3. So that's pretty straightforward. But it's important, I think, that you hear this and understand 2's complement. So 2's complement is another method. What I could do is look at the positive equivalent. So minus 93, I could say, well, I'll start with plus 93 and convert it like we know as 5 dog. So I have the 5 dog here. And then I take the 1's complement. A 1's complement is you simply swap true with false or 0 with 1's. So you swap them around. So I've got it lined up so you can see I've got 0 going with 1, 1 to 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0. So that is A2. Got A2. So now I take the 1's complement, I get A2, and then I add 1. I add 1 to get the A3. So that's how you can work with negation, and this is done in computers. This is how they do it. So they do the 1's complement, which is a very efficient computation because you're just flipping the bits. You do the 1's complement and then you increment. So very quickly you get the negative. All right, so I ran this just like this in script 6 and doing the bit complement of 93. And I have to tell it, for the bit complement, you got to tell it what size integer it is. So it did that, and it gave me, the first line gave me the able 2, and then the second line after I added 1, able 3. Very cool. Okay, so that is signed versus unsigned. The next thing is, you might recognize that sometimes that the numbers that you're holding in the computer, they represent text. Okay, and this is the hex table. So this is the most significant nibble here, and this is the least significant nibble. So let's take an example of capital A. Capital A is 41 hex, 41 hex. So if you can, and I don't know, it's a curse maybe, but I always remember the capital A is 41 hex. And once I know that, I can get all the rest of the capitals. No problem. Just add whatever I need to it. Okay. If I want lowercase a, I remember it's 61 hex. So I'm weird that way, but I can remember that. Pretty straightforward. The other one is if I want character 0 or any numerical character, I just have to remember that character 0 is at 30 hex, and then once I know that, then I know, well, I know 35 hex is 5. So it's pretty straightforward there. Other ones that are noteworthy: space is 20 hex. A carriage return is dog, 0 dog. A line feed is 0A. You see this a lot. You see a carriage return, line feed. So that within a text, so that kind of starts a new line. So you see this type of stuff all the time when you're looking at raw data. All right, so here's kind of what we're looking at. So the data, if integer thoughts are here, is infinitely accurate as long as you don't overflow, like I showed you that one example where you have 8-bit signed data and you go and add 1 to it. That's a rollover or an overflow. So that's kind of a caveat. As long as you don't overflow, then very accurate. Infinitely accurate. Okay. Then there's this weird thing, and this will take you years to get comfortable with this. I'm going to show you a little bit about that. There's a thing called Indianness, and it's a capital E, not an I, and it's just the way it is. But if I were to give you kind of a sequence of bytes, okay. So usually the data comes in 8-bit. It comes in sequence of bytes. So if I were to give you this sequence, And if you're like me and you remember that 41 hex is a capital A, that means that this is the B, that's a C, that's a D. So I've got a sequence of characters that's going to be capital A, B, C, D. And typically when you have a string, you'll want to put a 0 at the end. So that 0 there particularly will mean that that's the end of the string. So I've just got a sequence of 4 characters, A, B, C, D, and that's what it means. And for Indianness, this is a little weird. There's a thing called Little Endian, and what that means is that the lower byte comes first. The bytes come lower first and then increment up. So 16-bit Little Endian. So there's the A. So I have a 16-bit word. So I've got 2 bytes in a 16-bit word. The A is going to be the low byte. The B is going to be the high byte. The C is going to be the low byte of the next 16-bit word. And the D is going to be the high byte. Okay, I think I said that right. Get bits and nibbles and bytes and words. But I think I said that right. So let's try a 16-bit big endian. So that means that the A is going to be the high byte of the first word, and the B is going to be the low byte of the first word, and the C is going to be the high byte of the second word, and the D is going to be the low byte of the second word. I think I said that right. And then if it's 32-bit Little Endian, that means that you're going to be going A, B, C, D. A is going to be the low byte. B is going to be the second to low byte. C is going to come after that, and D is going to be the highest byte in the 32-bit word. Okay, 32-bit words are sometimes called double words or D words. So a word sometimes is referred to as 16-bit as a word. A double word is a 32-bit. Okay, and what can happen is if you go look at some raw data and you try to print out what they look like in hex, you may see that there's patches of zeros in there, because sometimes the program or the compiler that's placing your data, it may want to start data on a D word boundary. Okay, so I tried to create this little bit of intuition within you to notice these things, and once you get those, I mean, you're the master of your own world at this point. Okay, so integers can be used in a fixed point sense, and I'm going to show you what I mean by that in a minute when we actually look at some real applications of this. Okay, so now we're ready for real application, real implementation, and physical meaning. So here, this is something I did with Dr. Crane. We put a LiDAR. On the back of my van. We've got cameras. We've got GPS. There's the camera there. This is a webcam. We've got GPS on here, and we're going through. In this case, it's Sunrise Boulevard, Fort Lauderdale. So we did this project for the Florida Department of Transportation, and we're going down and we're trying to map how well the stripes are, and the stripes are looking pretty good here. And we're also trying to map how well the curbs are doing. So you see the curbs here, okay, and you see the stripes. So this is from Google Maps, so that's not our vehicle there, but my vehicle is going to be about right there, and we're going to be looking backwards, okay? So let's see what that looks like. So that's what it looks like. We're not going super fast, so this guy's trying to get around us. But you can see the stripes are in pretty good shape, just like I saw up there. The curb in pretty good shape, Now I want to show you what the LiDAR gave us. So it's it's like a radar, but it's using light instead. It's using light pulses going to target, and you're receiving range to target and reflectivity data out of that. So that's what it looks like. So we get this point cloud. This took a lot of calculations in order to patch this together. So we're getting scans of laser data, 8 megabytes per second, and we're putting together this map, and we're stitching it together based on sequential GPS locations. And it's not trivial at all. And then after we get the data, we go through and look at the reflectivity of our returns, and we go back and fill in the blue. So that's what my code did, is fill in the blue. And then here, to fill in the curb, I found the edge of the curb and put that as red, highlighted that as red. But this is very difficult to do this project, challenging. So here's what the sensor looked like, the Velodyne sensor. So it's doing some lasers. It's got different beams. It's got 16 different beams that's putting out as a swath, and then it's rotating around by what's called an azimuth. So it's rotating around with those 16 beams. So we get a range to target. We'll get the R value that comes back with corresponding to a particular beam coupled with a particular azimuth. So it's like spherical coordinates, right? So I think you understand that. Anyway, so let's look at this. So this is what the data comes back. So data comes back as 1,248 bytes. Okay, so the first 42 bytes will be a network header. So don't need to look at that. But in the last 6 bytes, there'll be a timestamp and some factory value. So we don't need to kind of concern ourselves there. But I'd like for you to check out how the data comes through in blocks. Okay, so you'll see azimuth. So azimuth N, there'll be a flag. So let's look for a flag that's going to be Foxtrot, Echo, Echo. So we're going to see a flag that's going to delineate the beginning of this data block. And then there's going to be an azimuth. And then we're going to start getting this firing sequence, or we're going to start getting data. It's going to be range to target coupled with the reflectivity. Okay, so let's see what that looks like. And this is raw data. Okay, so here it is right here. Data block 1 is starting with Fox, Fox, Echo, Echo, just like I showed you right here. Fox, Fox, Echo, Echo. Azimuth N should come next. So, all right, so we got that. And then check this out. So this is going to be Little Indian. I've got 3371, 3371. Those are hex. So let's go read it. All right, so example azimuth calculations. So we're getting to the 33 and the 71. It's Little Indian, so I got to flip them around. So I've got 7133 is the real 16-bit word. And that's going to be 7 times 4096 plus 256 plus 3 times 16 plus 3 is 28. It says it right there, convert to decimal, 28,979. And then they're saying that you divide it by 100, and that's going to be the resulting azimuth. That's going to be the direction that the data is going to be coming in at. And then there's some data coming through, range to target. So the first 2 bytes are going to be range to target, Little Indian, and then that 00 is going to be reflectivity. All right, so get the distance values. It's going to be 8959. Flip them around, and then you could do your own calculation, see that decimal. So this is fixed points. So each of those things means something. You multiply whatever number there. So each one means 2 millimeters. So you get the resulting 45,800 millimeters, which is 45 meters. So isn't that cool? So this all makes sense and something that you guys could do right now as you would look at this particular type of sensor. This is the most elaborate sensor I've seen, but all sensors are like this. They're very straightforward. So this is just talking about the calibrated reflectivity that was there. Okay, so So we've taken a look at integers. I think I've told you everything I know in 45 minutes. And now you are empowered to go forth and make something happen. I hope you've enjoyed it.